Alright, let's work on the second problem. Let's read it together. A 0.804 gram sample of an iron ore is dissolved in acid. The iron is then reduced to Fe2 plus ion and titrated with 47.22 milliliters of 0.02242 molar potassium permanganate solution. Calculate the results of this analysis in terms of A, percentage of iron, and B, percentage of iron 2,3 oxide. The balanced chemical reaction is provided here. So for every 1 mole of permanganate, it will react with 5 moles of iron 2 plus. But if you notice, this reaction is not between an acid and a base like in a typical neutralization titration. Instead, this is a redox titration. But even if it's a different type of titration, the principles of titration that we discussed earlier should still hold. For example, at equivalence point, there should be 1 millimole equivalent of permanganate for every 5 millimoles of equivalent iron 2 plus ion. So it shouldn't be that difficult. Let's try solving this problem. Let's write down the given. That's 0.804 grams. Sample containing iron. And then we process the sample by dissolving it in acid and then converting all the iron to iron 2 plus. We need to convert, by the way, all the iron to iron 2 plus because our chemical reaction that we will use in our calculation depends on iron 2 plus. So if we were not able to reduce all the iron 3 plus into iron 2 plus, our calculation will be wrong. So this step is necessary. We then know that this was titrated with 47.22 milliliters of 0.02242 molar potassium permanganate. We're asked to provide the percentage of iron and the percentage of iron 2,3 oxide. Now, we are asked to solve for percentage, right? So in this case, it makes sense to provide the percentage by weight because our sample is presented in terms of having a mass and not a volume. So that's 0.804 grams of sample. If we get the grams of iron or the grams of iron 2,3 oxide and divide that with the 0.804 grams of sample multiplied by 100, that should be the percentage of the analyte. So the calculation will closely resemble the first problem. Again, if I want percentage of iron, if the denominator is grams of sample, then the numerator should be grams of analyte or grams of iron. From our given, we know that if we multiply 47.22 ml and 0.02242 millimole per ml, we get the millimoles of potassium permanganate. And we know from the balanced chemical equation that 1 millimole of permanganate, so I'll remove the potassium so that you won't be distracted. The potassium was not included in the chemical reaction because it's a spectator ion. But again, going back to what I was saying, for every 1 millimole of permanganate, there should be 5 millimoles of iron 2 plus. Since we have millimoles, we can use the molar mass, right, to convert this into grams. Iron is 55.847 milligrams per millimole. Again, I want grams. So I'll just convert that directly by moving the decimal point 3 steps to the left. So for every 1 millimole of iron, there should be not 58.847 grams, but 0.055847 grams. Again, I just immediately converted the milligrams into grams. Notice though that although this is not ionic, the molar mass of the ion and the pure element should be similar because it's just a loss of electrons. So for consistency, I'll just write this as iron 2 plus. It is understood, however, that that is the molar mass. Now we have the grams of iron in the numerator. All we need to do is divide by the total sample mass, 0.8040 grams, and multiply everything by 100%. Taking my calculator, 47.22 times 0.02242 times 5 times 0.0055847 divided by 0.804 times 100%, the answer should be 36.77% of iron. Alright, so the process for letter B should be similar, right? Let me do that quickly. Percentage of iron 2,3 oxide. The start of the solution should be similar or comparable. 47.22 ml, 0.02242 millimole per ml. And based on the chemical equation, we still need to convert it into Fe2+. How will the Fe2,3 oxide or the iron 2,3 oxide come in? Just like our discussion in gravimetry, we need to convert the analyte into the desired form, and to do that we need to balance the analyte in the conversion factor. So if our goal is 1 millimole of Fe3O4, we need to balance iron 2 plus. Alright? We know that for 1 millimole of Fe3O4, that's 3 millimoles. So if we only have Fe, we need to multiply that by 3. Again, this is now 3 millimoles of iron, which is comparable to the numerator, that's 3 millimoles of iron as well. Again, just look at the analyte and trace how to balance it in your calculations. And again, we now just have to multiply by the molar mass. I'm now immediately converting it to grams once more. That's 0.23154 grams per 1 millimole. And I'm running out of space. Let me write times 100% over here and divide everything by 0.804 grams. Let me do that quickly in my calculator. 47.22 times 0.02242 times 5 divided by 3 times 0.23154 times 100 divided by 0.804. The answer is 50.81% iron 2,3 oxide. I hope this makes sense to you, and I'll see you in the final video.